Could this be the greatest illusion in the universe, where our very existence is built out of almost nothing? Right now, you're probably touching something. A chair, a desk, maybe your phone. It feels solid, certain, obvious. But according to modern physics, you are not actually touching it. In fact, nobody has ever touched anything, ever. And before this video ends, you'll understand why. Because the truth is far stranger than most science fiction. To understand why, we need to meet the simplest atom in the universe, hydrogen, the atomic equivalent of a single Lego brick, simple, tiny, yet hiding one of the biggest secrets in physics. A hydrogen atom contains just two main pieces, one proton in the center, one electron surrounding it. That's it. No complexity, no crowd. Just two particles. Now let's perform a thought experiment. Imagine taking the proton inside a hydrogen atom and enlarging it until it becomes the size of a tennis ball. A bright yellow tennis ball. Place it in the center of a football stadium. So where would the electron be? Not next to the tennis ball. Not somewhere in the stadium. Not even in the parking lot. The average distance would be more than 2 kilometers away. Over a mile. A 25-minute walk. Think about that. A tennis ball sitting alone. In the middle of an enormous, empty region. And somewhere, more than a mile away, is the electron. Everything in between? Empty. Almost completely empty. Fact is, atom contains 99.9999999999996% empty space. This isn't some unusual atom. This is hydrogen, the most common atom in the universe. The atom that powers the stars. The atom that makes up 62% of all the atoms in your own body. So, understanding hydrogen means understanding yourself. And hydrogen isn't special in this regard. Every atom is built on the same idea. A tiny nucleus, surrounded by vast regions of apparent emptiness. And that leads to a startling realization. You are mostly empty space. Your skin, your muscles, your bones, your brain. Overwhelmingly empty space. The chair beneath you, mostly empty space. The walls around you, mostly empty space. Mountains, oceans, skyscrapers, entire planets. Mostly empty space. And now we can finally return to one of the strangest facts in all of science. Imagine removing all that empty space. Not the particles, just the empty space. Do it for every atom in your body, then every atom in every human being on Earth. Every man, every woman, every child. All 8 billion of us. The entire human race. The result? The entire human race would fit inside a single sugar cube. A cube barely 1.5 centimeters wide. Small enough to balance on your fingertip? Pause for a second. Imagine that. 8 billion people. Compressed into something. You could balance on your fingertip. And here's the truly absurd part. That tiny cube would still weigh nearly 500 million tons. Hundreds of millions of cars. Packed into something you could hold in one hand. And yet, nothing around you behaves as though it's empty. Your chair supports your weight. Walls stop you in your tracks. Steel feels impossibly hard. The floor prevents you from falling through the earth. The world feels solid, stubbornly solid. So how can something that's almost entirely empty feel so real and solid? Why can't we walk through walls? Why doesn't sunlight pass straight through your hand? Why doesn't your body collapse into itself? And if matter is mostly empty space, what exactly are you touching right now? To answer that, we need to take a journey into one of the strangest stories ever uncovered by science. The story of the atom. And how every generation of scientists discovered that reality was far weirder than anyone imagined. Think about the atom for a moment. What picture appears in your mind? A tiny nucleus in the center. Electrons circling around it, like planets orbiting the sun. You've probably seen that image hundreds of times. In textbooks, in classrooms, on science posters, maybe even in a company logo. It's one of the most recognizable symbols in science. There's just one problem. It's wrong. Or at least, it's not the full story. The history of atomic theory is really the story of humanity repeatedly discovering that reality is stranger than expected. Every time scientists thought they understood matter, nature revealed another surprise. And another, and another. Our story begins over 2,400 years ago, long before laboratories, long before microscopes, long before modern science even existed. A Greek philosopher named Democritus asked a simple question. If you keep cutting something in half, could you do it forever? Or would you eventually reach the smallest possible piece? Democritus believed you would. He called these tiny building blocks atomos, meaning uncuttable, indivisible, atoms. No experiments, no evidence, just a brilliant hunch. Astonishingly, that idea survived for over 2,000 years. Then in 1803, science finally entered the story. A British chemist named John Dalton noticed something curious. Chemical reactions followed strict rules. Elements always combined in precise ratios. The numbers were too perfect to be random. Dalton proposed a bold explanation. Matter must be made of tiny particles, tiny solid spheres, tiny billiard balls, indestructible, featureless, simple. For the first time, atoms moved from philosophy into science. But nature wasn't finished surprising us, not even close. In 1897, a physicist named J.J. Thomson discovered something impossible. Atoms weren't indivisible after all. They contained smaller particles, electrons. Suddenly, the atom had internal structure. The solid billiard ball was gone, shattered. To explain this new discovery, Thomson imagined the atom as a positively charged blob. Electrons were scattered throughout it, like raisins inside a pudding. Scientists actually called it the plum pudding model, which sounds less like physics and more like dessert. But at the time, it was revolutionary. Then came one of the most important experiments in scientific history. An experiment so shocking, it changed our understanding of matter forever. In 1911, Ernest Rutherford fired tiny alpha particles at an ultra-thin sheet of gold. The idea seemed straightforward. If Thomson's model was correct, the particles should pass straight through because the pudding is soft and the raisins are tiny. They are no match for the high-speed alpha particles. Maybe deflect a little. Nothing dramatic. Most of them did pass straight through, but a few behaved strangely. A tiny number bounced almost straight back, as if they had struck something incredibly dense. Rutherford later said it was like firing a cannonball at a sheet of tissue paper and having it bounce back at you. Something was hidden inside the atom, something tiny, something dense, something carrying almost all its mass, the nucleus. And just like that, the universe became emptier, much, much, much emptier. Because Rutherford realized something astonishing. If most alpha particles could pass straight through, then most of the atom had to be empty space, vast regions of emptiness, surrounding a tiny central nucleus. The first clue that matter wasn't nearly as solid as it seemed. A few years later, another scientist arrived with a new idea, Niels Bohr. Bohr suggested that electrons could only occupy specific energy levels, like standing on the rungs of a ladder. You can stand on one rung, or the next, but not halfway between them. To move from one level to another, the electron had to make a sudden jump, absorbing or releasing light in the process. Different jumps produce different colors. Suddenly, many mysteries of chemistry and physics began making sense. And this model became famous. Very famous. In fact, it's probably the image you're picturing right now. The miniature solar system atom, electrons orbiting the nucleus. Neat, organized, easy to understand. But reality had one more surprise waiting, and this one was bigger than all the others. Because in the 1920s, scientists discovered something so strange that even today it feels impossible. The electron isn't really orbiting anything, at least not in the way planets orbit the sun. The neat little planetary atom began to fall apart, and what replaced it was far stranger, far more beautiful, and far more difficult to believe. Welcome to the quantum world, the place where reality begins to defy common sense. In 1926, an Austrian physicist named Erwin Schrödinger developed a revolutionary equation, an equation that would completely change our understanding of matter. And what it revealed was astonishing. The equation didn't tell scientists where an electron was. Instead, it told them the probability of where they might find it. Not certainty, probability. Not location, possibility. This may sound like a small difference. It isn't. It's enormous. Because it means electrons are not tiny marbles flying around the nucleus, at least not in the way we imagine. Instead, they exist as something called a probability cloud, a region of space where the electron is likely to be found. Some areas are more likely, some less likely, but there is no tiny planet tracing a neat circular path. The cloud isn't simply hiding the electron's location. According to quantum mechanics, the cloud itself is the most complete description of reality we have. And this creates one of the most unsettling ideas in all of science. Before a measurement is made, the electron does not seem to occupy a single location. It behaves as though multiple possibilities exist simultaneously. And yes, this is where things start sounding like science fiction. Because one famous interpretation of quantum mechanics suggests that every possible outcome may unfold in its own parallel reality, a vast collection of branching universes, existing side by side, invisible to one another. This idea is known as the many worlds interpretation. It sounds completely absurd. Even many physicists struggled to accept it. Some still debate what it truly means. Yet experiment after experiment keeps confirming the predictions. Again, and again, and again. Quantum mechanics is now one of the most successful scientific theories ever created. Its predictions are accurate to astonishing precision. The smartphone in your pocket, the computer you're watching this on, modern lasers, medical imaging, all of them depend on quantum mechanics being correct. Reality doesn't care whether something feels intuitive or otherwise. It only cares whether it's true. And the deeper scientists looked, the stranger things became. Because the electron cloud doesn't have a sharp edge. There is no exact point where the atom suddenly stops. The atom has no solid outer wall, no microscopic shell, no precise border separating the inside from the outside. It simply fades into space. Think about a cloud in the sky. Can you point to the exact place where the cloud ends? Not really. It gradually fades away, dense in the center, thinner near the edges, eventually blending into the surrounding air. Atoms behave similarly. There isn't a perfectly defined boundary, no hard shell, no outer wall, no cosmic fence. The atom simply fades outward, its electron cloud becoming less and less likely, but never truly ending. In a sense, atoms are less like tiny solar systems, and more like ghostly clouds, clouds of possibility, clouds of probability, clouds that somehow build everything around us. Your body, your chair, your house, entire mountains, entire planets. Everything is built from these strange quantum clouds. Reality, at the quantum level, stops obeying common sense, which is why schools still teach the outdated Bohr model. It's just way easier to visualize. And now another mystery appears, an even bigger one. If electrons are spread out like clouds, if atoms are mostly empty space, if matter has no hard boundary, then why does a wall look solid? Why can't light pass straight through it? Why doesn't your hand simply drift through a table? To answer that, we need to understand something even stranger than the electron itself. Because the reason matter appears solid has almost nothing to do with solidity and everything to do with light. The next chapter of our story begins with a simple question. What does an atom actually look like to light? Now we finally arrive at the real mystery. After all, if an atom is mostly empty, shouldn't light simply pass through the gaps? Shouldn't everything be transparent? Yet the world doesn't look transparent. It looks solid, colorful, opaque, real. So what's going on? The answer begins with light itself, because we need light to see things around us. Imagine you're standing outside a chain-link fence. If you throw a basketball at it, the ball hits the wires. It can't fit through the holes. Now imagine throwing a grain of sand. The grain slips right through, no problem. Whether something passes through a gap depends on its size. And surprisingly, the same idea applies to light. Visible light travels as electromagnetic waves. And these waves have a characteristic size called wavelength. The wavelengths of visible light range from roughly 400 nanometers to 700 nanometers. That sounds tiny, and it is. But compared to atoms, it's enormous. A typical atom is only about 0.1 nanometers wide, thousands of times smaller than the wavelength of visible light. Imagine trying to read a street sign from an airplane. The sign is still there, but the details are simply too small to be read. Visible light faces a similar problem when it encounters atoms. Its wavelength is far too large to resolve individual atomic gaps. Its wavelength is thousands of times larger than the structures it's trying to see. So instead of revealing individual atomic gaps, it interacts with vast collections of electron clouds all at once. And that's where electrons become the stars of the story. Remember those probability clouds surrounding every atom? Those clouds carry negative electric charge, and light is extremely sensitive to electric charge. When light encounters matter, it doesn't fly effortlessly through empty atomic space. Instead, it encounters vast forests of electron clouds. The electron clouds look like a solid wall to light an electromagnetic barrier. Some light gets absorbed, releasing heat energy. When light gets absorbed, we see darkness. Some gets scattered, some gets reflected. This scattering and reflection is what makes the atom visible. A red apple reflects wavelengths we perceive as red. A green leaf reflects wavelengths we perceive as green. A mirror reflects light so efficiently that it produces a clear image. A black shirt absorbs most incoming visible light. Different materials interact with light differently, but in every case, electrons are doing the heavy lifting. The world isn't visible because atoms are solid. The world is visible because electron clouds constantly interact with light. Because visible light only shows part of the story, a very small part. The light your eyes can detect occupies a tiny slice of the electromagnetic spectrum, a narrow window, a tiny band of reality. Beyond that window exist many other forms of light: radio waves, microwaves, infrared, ultraviolet, X-rays, and at the extreme end, gamma rays. Gamma rays are different, very different. They possess incredibly short wavelengths, far shorter than visible light, and they carry enormous amounts of energy. Imagine trying to navigate a dense forest. A giant beach ball would constantly collide with the trees. It couldn't move very far. But a tiny needle? The needle could slip between branches much more easily. Gamma rays behave somewhat like that needle. Their extremely short wavelengths allow them to probe structures that visible light cannot resolve. They reveal details hidden from ordinary sight. And what they reveal is astonishing. Matter is not the impenetrable fortress it appears to be. Far from it. To gamma rays, atoms expose their emptiness. the vast spaces between nuclei become impossible to ignore. This is why gamma radiation can pass through your body, through walls, through materials that appear completely solid. The emptiness was always there. Your eyes simply couldn't see it. In fact, this property makes gamma rays incredibly useful in medicine. Doctors can direct highly focused gamma ray beams toward a tumor deep inside the body. Individual beams pass through healthy tissue with minimal damage, but where hundreds of beams converge, their combined energy can destroy cancer cells with remarkable precision. We call this stereotactic radiosurgery, but despite everything we've learned, there is still one final mystery, the biggest mystery of all. Right now, your body feels solid. The chair beneath you feels solid. The floor feels solid. Why? Why can't your hand pass through a table? Why don't you fall through the floor? Why does anything feel hard? The answer is about to overturn one of the most basic assumptions you've held your entire life. Because the truth is, you have never touched anything. Not once, not ever. Think about that. Every handshake, every hug, every high five, every time you've held someone's hand, every time you've patted a dog, every time you've picked up a coffee mug, every time you've pressed a key on a keyboard, it felt like contact. But according to physics, the atoms never actually touched. Because when your hand approaches a table, something remarkable happens. The atoms in your skin approach the atoms in the table, closer and closer and closer. But before the atoms can actually overlap, an invisible barrier appears. A barrier created by the very electrons we've been talking about throughout this story. And understanding that barrier may completely change how you think about touch itself. Remember this. Electrons all carry the same electric charge, negative, and like charges do not get along, they repel. It's the same reason two identical poles of a magnet push away from each other. Try forcing them together, they resist. The closer they get, the stronger the repulsion becomes. The same thing happens between electron clouds. As they approach one another, electromagnetic forces begin pushing back, hard. That's electrostatic force field repulsion, and it has a name, Coulomb's law, a classical physics law, and that's only the beginning. Because quantum mechanics has another rule, a rule so fundamental that entire stars depend on it. It's called the Pauli exclusion principle, and it states something remarkable. No two electrons can occupy exactly the same quantum state at the same exact time. Think of it like a theater. Every seat is assigned. Every ticket is unique. No two people can sit in the exact same seat at the exact same time. Electrons obey a similar rule. Nature simply refuses to let them pile into the same state. As atoms are squeezed closer together, their electrons are forced into higher energy levels, creating a powerful outward pressure. This quantum resistance is known as Pauli repulsion, and it becomes enormous at very short distances. So when you press your hand against a table, the atoms never merge. They never pass through one another. They never truly make contact. Instead, billions upon billions of electromagnetic interactions push back simultaneously. In a sense, your feet are not truly touching the floor, which means you are levitating all the time. Reality is less like a world of tiny solid particles and more like a vast web of invisible forces, endlessly pushing, pulling, balancing, shaping everything around us. And if that sounds strange, it gets even stranger, because the solidity you experience every day exists almost entirely inside your brain. Your nervous system receives electrical signals. Your brain processes them, and then it constructs an experience, an interpretation, a model of reality. Your brain interprets this electromagnetic resistance as the sensation of touch, What you feel as texture, pressure, hardness is actually just force, not contact. You don't directly experience atoms. You don't directly experience electrons. You don't directly experience electromagnetic fields. You experience your brain's translation of them. The feeling of wood, the feeling of metal, the feeling of silk, the feeling of stone. All of these sensations emerge from invisible interactions occurring far beneath conscious awareness. And yet, despite all this weirdness, the illusion works perfectly, every day, every second, for your entire life. Which brings us to the final and perhaps most astonishing realization. The deeper we zoom into reality, the less solid reality becomes. Matter is mostly empty space. Atoms are mostly empty space. Electrons exist as probability clouds. Light creates the appearance of solidity. Touch is the sensation of force, and nothing truly makes contact. The world feels permanent, yet beneath the surface, it is a dance of probabilities, fields, energy, and emptiness. The chair you're sitting on, the screen you're watching, the hands you're holding, the stars above your head. Everything emerges from structures that are almost entirely empty. And somehow, from all that emptiness comes color, comes sound, comes life, comes love, comes memory, comes you. Perhaps that's the strangest discovery of all. The universe doesn't build reality from solid things. It builds reality from almost nothing. And from that near nothingness, it creates everything. So the next time you place your hand on a table, remember this: you are not touching it. You never have. And yet, somehow, the universe makes it feel as though you are. And maybe that's the greatest illusion reality has ever created. If you find this video enlightening, please consider subscribing the channel and like the video. Now, do you believe you have never truly touched anything? Let me know in the comments below.